Hey guys, it's Mr. Covey here, and today we're going to go over how to factor quadratics when we have a number out in front of our x squared term. Okay, so it's a little trickier. But before that, I wanted to review a problem like this, which was like the problems that were just on that little mini quiz you took. Okay, so we're trying to solve this equation. It has a squared term, an x term, and a number. It's all equal to 0. We are going to try and factor it to solve it, and then use our zero product property. So since we have an x squared here, we're going to have an x as the first term in both of our binomials. And then we got to figure out two numbers to put here and here that multiply to 10 and add to 7. So sometimes I like to go over to the side and say, what are some things that multiply to 10? Well, I got 1 and 10, I got 2 and 5, and that's about it. Do either of these add to 7? Perfect, that does. So those are going to be the two numbers that I put there. And now I've factored my quadratic. To actually figure out what x's make this equation true, I set each binomial equal to 0. Because either of them being 0 will make this whole left side equal 0. Solve those little equations, and I get my two solutions. Okay, so that's what we've been doing so far. What I want to look at today is how to factor when there's a number out in front of x squared that's not just 1. Okay, so the process is similar, but there's a couple of differences. If you want to write down some steps over here, I left you some space here. So I'm not going to write them down, but if you want to write down some steps, I definitely recommend it. Okay, so we're factoring a quadratic here where this first number is not just 1. There's actually a number in front of the x squared term. So our goal is still the same. We want to write it as two binomials. So it's going to look like this at the end. To start, we don't look for two numbers that multiply to 12 and add to 17. To figure out what we want our numbers to multiply to, we actually multiply our coefficient in front of our x squared term by our constant at the end. So we do 6 times 12, we get 72. That's what we're looking for, two numbers that multiply to 72 and add. We still want them to add to our middle term. So let's start making a list of numbers that multiply to 72, and we're looking for two that add to 17. So I think 36 and 2, 18 and 4, 9 and 8. And as I'm making my list, I'm checking, do they add to 17? No. Do they add to 17? No. Do they add to 17? Yes. Here are my pair that work. Now I still have a little more work here, which is a little different than before. So now that I found those two numbers that multiply to 72 and add to 17, I do what's called splitting the middle term. So I split that 17x into 9x and 8x. And then I bring down the 12 and the 6x squared. Okay, so I've split that middle term. Now I group together the first two terms, and I group together the second two terms, and I see if I can take something out of both of those. So if I have a 6x squared and a 9x, what can I take out of both of those? Well, they both have an x term, and they're both divisible by 3 as well, so I can factor out a 3x. I'm left with 2x and 3. And I'm going to do something similar for the second thing. What can I take out of 8x and 12? Well, I can't take an I can't take an x out of both of them, but I can take a 4 out, because 12 and 8 are both divisible by 4. What I'm left with is 2x plus 4 times what is 12? It's 4 times 3. And now something good happened. So when I'm doing factoring like this, the fact that these two things are the same is good. That tells me one of my binomials. One of my binomials is 2x plus 3. The other one, I get from what I factored out of these two pairs. So I factored out a 3x and a 4. So the way this factors is 3x plus 4 times 2x plus 3. And I'm done. Again, I can always check this by distributing out or foiling these two binomials and seeing if I end up back here. Because again, factoring is just the reverse process of distributing. Okay, I'm going to go through two more examples here. So it's a quadratic where the coefficient on the x squared term is not just 1, it's 2. So I'm going to multiply that by negative 20 to get negative 40. Looking for two numbers that multiply to negative 40 and add to 3. So I'm like negative 40 and 1, negative 20 and 2, negative 8 and 5. When one's negative and one's positive, remember I have to try both combinations. So maybe it's like 8 and negative 5. All right, so I look through these, saying, do any of these add up to 3? Nope. Nope. This adds up to negative 3, so it seems close, but it's not exactly right. Flip those signs. 8 and negative 5 add up to negative 3. So now I know how I'm going to split that 3x. I'm going to split it into an 8x and a minus 5x. Going to bring down the 2x squared. I'm going to bring down the minus 20. I'm going to group together the first two. I'm going to group together the second two. I'm going to take a greatest common factor out. Let's see what I can take out of both of these. They both have an x. They're both divisible by 2. I will take out 2x. 2x times what is 2x squared? Just x. And I'll have a 4 to get the 8x. What can I take out of both of those? Well, they're both negative. And I can also take a 5 out of both of them. I'm left with x. Negative 5 times what is negative 20? Well, positive 4. So then it must factor to 2x minus 5 times x plus 4. And remember that the difference between this one and the previous one is that this is actually an equation. It's not just asking me to factor, it's asking me to solve this equation. So factoring is actually only the first part. Now that I factored it, I need to use that same idea that we've been using, that zero product property. So if these two things multiply to equal 0, then either this equals 0 or this equals 0. So I'm going to get my two solutions by setting x plus 4 equal to 0. That will give me one solution, and then I'm going to set 2x minus 5 equal to 0 to get the other solution. Solve those little equations. I get 5 halves and negative 4 as my two solutions to the equation. Again, this one was an equation, so factoring was something that helped us solve the equation. Okay, let's look at one more example here. The difference here I want you to notice is that it's not all equal to 0. So before we do anything, when we're solving a quadratic, it's always a good idea to make sure that it's equal to 0. Oops, it's a little... Okay, so now it's all equal to 0. And I can try and factor it. Multiply 3 and negative 4 to get negative 12. What multiplies to negative 12 and adds to 11? Well, I'm going to think of some things that multiply to negative 12. Does this add to 11? No. Yes, this works, and that... Oh, that's the same thing. So 12 and negative 1 multiply to negative 12 and add to 11. So I'm going to split my middle term. 12x minus 1x. Bring down the negative 4 and the 3x squared. Still all equal to 0. Group together the first two terms. Group together the second two terms. See what I can factor out of the first two. I can take out an x. I could also take out a 3. I'm left with x plus 4. Out of the second two, no, they're both negative at least, so I'll take out a negative 1, left with x plus 4. Again, you know you're factoring right when those second two parts are the same. If they're not, something went wrong. Let's go back up over here. So it must factor as 3x minus 1 times x plus 4, and it's equal to 0. Okay? And now I just use my zero product property like we have been. Set each one of those individually equal to 0 to get my two solutions. Sorry, I went off the page there. I get negative 4. I get 1/3. And those are my two x values. Those are the two solutions to this equation. Again, remember, of course, I could plug those in for x and see that 3 times negative 4 squared plus 11 times negative 4 does in fact equal 4. And same if I plugged in the 1/3. And that concludes this video.